The introduction of military aircraft in the first decades of the 20th century changed the face of warfare. The speed at which attacks could come from the air meant that armies had to develop means of detecting incoming bombers as early as possible. Initial experiments sought to identify the noise of aircraft engines at a distance. Working like giant ear trumpets, listening horns gathered and concentrated on faint sounds. Never particularly effective, acoustic detection systems were quickly outclassed by electronic systems, which bounced radio waves off targets and detected the echoes. This came to be known as radar. Like the British, Americans, and others, the Germans started developing radar in the 1930s. In World War II, radar was the cornerstone of the German air defense system. Powerful ground-based systems provided the initial data, which allowed controllers to direct fighters into the right areas to attack the bomber formations. Night fighters with their own radars could detect and close on bombers even in total darkness. But it was the British who were the first to make effective use of radar for air defense purposes. In the Battle of Britain, radar provided the warning that allowed fighters to be dispatched to the right interception points and belts of anti-aircraft guns to be readied around likely targets. At control centers, visual sightings were correlated with radar data to create a high-quality indication of the German raid's timings and likely target. The fighter squadrons best able to make an interception were scrambled to the right position and height to make an attack on advantageous terms. The initial system was codenamed Chain Home and was composed of a string of coastal stations, each based on tall masts carrying the transmitter and receiver antennas. The Chain Home system was able to detect only higher altitude targets at ranges out to 120 miles or more. This gave time for the control system to collate the various data it received and order the launch of the relevant squadrons. The system was limited in capability and prone to failures and mistakes, but it could be rushed into service to provide a capability not previously available. The tall transmitter and receiver towers were very obvious and became targets in the Battle of Britain. But they proved difficult to destroy, and the damage was repaired easily. The major failing of the Chain Home system was its inability to detect low-level targets. This led to the creation of the Chain Home Low Radar Net. It operated at a lower wavelength and used a rotating antenna. The pairing of Chain Home and Chain Home Low provided the British with an all-altitude detection capability. Throughout World War II, British radar development was constant and rapid. Ever-improving ground-based radars were developed. Greater technical know-how also allowed radars to be made smaller, and by 1940, the first airborne interception radars were installed in fighters. Like their ground-based counterparts, the airborne radars were developed enormously in World War II. If an enemy is using radar equipment, a determined opponent will try to hamper or destroy that ability. This was as true in World War II as it is today, and the British proved very adept in this secretive skill. Now known as chaff, window was the code name for bundles of metallized strips dropped by bombers to break apart in the air. As they fluttered slowly to the ground, the strips reflected radar energy and filled the German screens with false echoes. Mandrill was the code name for an airborne noise jammer to counter the German Freya radar. It radiated signals to swamp the normal return echo, which obliterated formation size and range information. Moonshine was the code name for equipment that made one aircraft seem like many planes, which forced the Germans to divert fighters that could have been used to greater effect elsewhere. The Germans, British, and Americans used airborne interception radars most effectively. Early equipment was bulky, unreliable, and lacked both range and precision. Later equipment was much more reliable and effective. Their range was always limited, though, and radar-equipped night fighters were generally vectored into the vicinity of enemy aircraft by a ground controller, getting information from larger land-based radar equipments. Air-to-surface radars underwent the same type of development. These were developed from limited-range equipments able to detect only larger targets to longer-range equipments able to detect smaller ones. By the end of World War II, airborne radars could detect the snorkels of German U-boats. A parallel development in the electromagnetic spectrum was the system for detonating magnetically triggered sea mines from the air. This is a Vickers-Wellington twin-engine bomber with a large duralumin hoop. When energized from a power source in the aircraft, the hoop generated a magnetic field strong enough to trigger a mine, which might otherwise have been initiated by a ship's hull. The FUG-200 was a German radar used in the air-to-surface search role at sea. The radar was very capable, and the plane became known by the massive antennas on its nose and wing. The inevitable drag burden was more than offset by the capabilities offered by the radar, which was one of the best of World War II. The Heinkel HE-111 was one of Germany's most important twin-engine bombers of World War II. Though not as versatile as the Junkers Ju-88, the HE-111 could carry considerable weight and volume over a useful range. It was used for a number of special purposes. Here, the type is seen with the Henschel HS-293, a pioneering air-launched anti-ship missile. The HS-293 was rocket-propelled for a range of 9,300 yards when released at an altitude of 16,400 feet, and was guided onto its target via radio signals transmitted from the operator's position in the bomber. Knickerbine, which means crooked leg, was a radio navigation system used by the Germans early in World War II to aid bomber navigation. It was a development of the Lorenz landing aid and created a system in which a Pathfinder bomber could fly down the line of a radio beam. Any deviations from the course were indicated to the operator by a change in the pitch of the signal. Larger antennas with much smaller beam angles were set up, and broadcast power was increased considerably. The first two of these new Knickerbine transmitters was set up in northern Germany near the border with Denmark, and the other to the south near France. The two beams could be pointed to cross over the target, and the bomber would fly into the beam of one and ride it until it started to hear the tones of the other. When the steady, on-course sound was heard from both radios, the bomber knew it was over the designated target and dropped its bombs. However, the bombers could easily be fooled to dropping their bombs onto empty fields. Spoofing methods were as simple as lighting fires to simulate a burning town. The system was also easy to jam or decoy once its basic operating method had been determined. Oboe was the code name for a British navigation and bombing system used by de Havilland Mosquito and Avro Lancaster Pathfinder aircraft. Two stations at different locations many miles apart in England each transmitted a signal to the Pathfinder bomber, which carried a radio transponder. The transponder reflected the signals, which were then received by the two stations. The round-trip time of each signal gave the distance to the bomber. Each oboe station used the radio ranging to define a radius, with the intersection of the two circles pinpointing the target. The Mosquito flew along the circumference of the circle defined by one station, known as the Cat, and dropped its load, either bomb or flare markers, when it reached the intersection with the circle defined by another station, known as Mouse. There was a network of oboe stations over southern England, and any of the stations could be operated as a cat or a mouse as needed. The best night fighter of World War II was arguably the Mosquito in one of its many specialized forms. It was fast, agile, powerfully armed, and had long range. Just as important, it was developed in parallel with a series of British and American airborne radars of increasing capability. The Mosquito night fighter eventually became an offensive warplane, flying with bomber streams to search out and destroy German night fighters. Introduced to service late in World War II, the three-seat Northrop P-61 Black Widow was the U.S. Army Air Force's counterpart to the Royal Air Force's two-seat Mosquito night fighter in its later variants. Carrying powerful armament and effective radar, the Black Widow could also operate in the night intruder role with a sizable bomb load. In common with most other military systems, the pace of electronic development slowed some after the end of World War II. The emergence of the USSR as a superpower prompted the U.S. to step up its efforts. At the time, the U.S. was the world leader in electronic systems and saw advanced electronics as a means to maintain a technical superiority over the USSR. Radar capability and reliability were enhanced, and the development of the first computers allowed ground-controlled interception to be improved. The Semi-Automatic Ground Environment, or SAGE, was a system used with fighters such as the Convair F-102 to speed the interception process and make it more accurate. In this system, computers worked out and transmitted optimum interception courses for dedicated interceptors. Sometimes these were equipped with nuclear-armed rockets to ensure the destruction of bomber forces that might be carrying nuclear payloads. Ground-based defenses, with missiles supplementing anti-aircraft guns, remained a major threat to fighter bombers and attack aircraft operating over the battlefield. The Fairchild Republic A-10 Thunderbolt anti-tank warplane was designed for battlefield survivability, and it is seen here releasing flares to confuse the guidance systems of missiles using infrared homing. Battlefield operations must be flown at low level, increasing the threat from ground-based weapons such as massed anti-aircraft artillery and surface-to-air missiles. The ability of the U.S. Navy's carrier-borne air arm to attack land as well as sea targets was a decisive factor in World War II. This capability was enhanced during the 1950s and 1960s with the introduction of naval warplanes that were just as capable as their land-based counterparts. These aircraft grew steadily in the sophistication of their electronics for defensive as well as offensive purposes. This paid excellent dividends in Vietnam in the 1960s. Initially, in this conflict, naval aircraft proved more vulnerable than their U.S. Air Force counterparts. However, the introduction of new equipment reduced that vulnerability. The predecessor of the Hornet series in U.S. Navy service was the Grumman F-14 Tomcat. The front seater was the pilot, and the rear seater was the RIO, or Radar Intercept Officer, who controlled the all-important radar and the offensive and defensive electronic warfare systems. Here, the crew of a Tomcat fleet defense fighter check out their aircraft before a flight. The Tomcat's AWG-9 fire control system had a massive radar with the raw transmitter power to burn through an enemy's electronic defenses. This allowed the radar to find and lock onto a target at long range. This process of increased electronic defense and offense led to the development of aircraft such as the Grumman EA-6 Prowler. This was created for a dedicated electronic attack role to protect packages of attack aircraft. Now, in the later stages of a long career, the Prowler was developed from the A-6 Intruder two-seat medium attack warplane into a four-seater with the ALQ-99 tactical jamming system. Able to extend its flight endurance by refueling from aircraft such as the KC-10 Extender using the probe and drogue system favored by the U.S. Navy, the Prowler can accompany attack aircraft packages deep into enemy territory. However, one of the Prowler's most significant limitations has been its subsonic performance. The type was designed to accompany other subsonic aircraft, such as the Intruder, the Douglas A-4 Skyhawk, and Vought A-7 Corsair II. These were replaced by more modern types, such as the Boeing FA-18 Hornet and improved Super Hornet with supersonic performance. It then became more difficult to schedule missions in which the capabilities of both types could be utilized fully. The answer, now on the verge of first-line service, is the EA-18 Growler. This is a development of the Super Hornet, similar to the Prowler development of the Intruder. The Prowler's electronic warfare capability is centered in the ALQ-99 system, operated by 3 of the 4-man crew. In the Growler, it has been repackaged and updated to allow it to be operated by just 1 person. The large pod at the head of the Prowler's fin carries an array of receiving antennas. The signals received by these are fed into the ALQ-99 system's central digital computer for display and recording. The identity, bearings, and jamming frequencies of the emissions are then analyzed automatically, semi-automatically, or manually by the system's operators. Finally, any one of the 5 external and completely self-powered jamming pods is activated to jam the desired frequency. Each pod covers one of the main radar frequency bands and contains 2 powerful jammers. Steady evolution of the ALQ-99 system has kept the Prowler ahead of all current threats throughout its long life and a number of conflicts. These have included the 2 Gulf Wars and the campaign in Afghanistan. The Prowler can operate from the U.S. Navy's large aircraft carriers and also from land bases. The Prowler is operated by squadrons of the U.S. Navy and U.S. Marine Corps, but crews often include personnel from the U.S. Air Force, as the Prowler supports USAF operations. The Air Force currently lacks a dedicated electronic attack aircraft. The Air Force counterpart to the Prowler was the EF-111 version of the General Dynamics F-111 Strike Fighter. Developed largely by Grumman, the Raven was generally known as the Electric Fox or Sparkvark, which was a reference to the original F-111's Aardvark nickname. The EF-111A was designed to replace the obsolete Douglas EB-66 in a program allocated to Grumman. It was the first of 42 such conversions with the ALQ-99 system and entered service in 1981. The aircraft were retired in 1998 after they became too expensive to maintain. This may have saved the Air Force money, but it cost them a unique electronic warfare capability, as the Spark-Vark offered high supersonic performance and long range. This meant that the EF-111 could accompany supersonic warplanes all the way to and from their targets. Before opting for the EF-111, the Air Force had considered the Prowler, but it was reluctant to adopt a subsonic U.S. Navy type. However, following the EF-111's retirement, the Air Force has been forced to depend on the Prowler for electronic warfare. Here, members of an EF-111's ground crew inspect the bay for the aircraft's electronic countermeasures, or ECM, and remove a spent canister from the bay next to one of the engines. Once removed, a pair of ground crew members fit a fresh canister into the special bay. These canisters carry chaff and flares to help protect the aircraft from surface and air-launched weapons using radar and infrared guidance. The pilot, electronic warfare officer, and crew chief undertake the standard pre-flight inspection of their EF-111 to ensure that there are no loose panels, leaks of fuel or hydraulic fluid, that the flight control surfaces are in no way impeded, and all stores are firmly attached. The Electronic Warfare Officer, or EWO, stores his mission gear in the side of the side-by-side cockpit, and both members of the crew enter the cockpit and start their pre-flight checks. The crew chief and other ground personnel move below and around the aircraft as the paired engines are run up and the control surfaces are moved and checked. The Spark-Vark lifts off in full afterburner. The tasks of the EWO during the mission are essentially inside the cockpit, where he watches his displays. Electronic attack is usually adequate on its own, but on other occasions, a physical attack is required. Here, an AGM-88 high-speed anti-radiation missile, or HARM, is carried under the wing of a Prowler alongside an ECM pod. The AGM-88 is designed to complete its mission in the shortest possible time to avoid giving its target time to move or shut down. Here, such a missile strikes the bridge of a ship target, though the typical target is the antenna of a surface-based radar system. An F-16 launches an AGM-88 and an example of its predecessor, the AGM-45 Shrike, over a desert test range. This is an MC-130 variant of the Lockheed Martin Hercules transport for the Special Forces support role, which carries an ALQ-8 jammer pod under its wing for ECM purposes. The Big Crow is a Boeing NKC-135 assigned to flying testbed duties for electronic warfare equipment. Testbeds are trials platforms, which are important to ensure that computer programs and other equipment perform well under operational conditions. In its research and development tasks, the aircraft has appeared in several forms and is seen here deploying a trailing wire antenna. The pace of development in offensive electronic warfare and countermeasures counterpart is fast. The rapid prototyping and evaluation of experimental systems are essential to maintain the speed of development and catch errors before they are built into more tightly packaged systems. The use of aircraft such as the NKC-135, with its considerable weight and volume-carrying capability, allows the flight testing and validation of such systems before they are prepared for production. The North American Aerospace Defense Command, or NORAD, is a joint organization of the U.S. and Canada that provides airspace warning and control for North America. NORAD was established in May 1958 as the North American Air Defense Command. Since 1963, NORAD's main technical facility has been the Cheyenne Mountain Operations Center in Colorado. For this reason, NORAD is sometimes unofficially referred to as Cheyenne Mountain. Here, U.S. and Canadian technicians keep watch over North American airspace at displays fed by radars strategically located on the ground and in the air over the North American continent and the waters around it. The Distant Early Warning, or DEW line, was a system of radar stations in the far north of Canada, with additional stations along the north coast and Aleutian Islands of Alaska, as well as the Faroe Islands, Greenland, and Iceland. The remote radar stations of the DEW line were built with great difficulty because of their Arctic locations. The radars of this line were used to warn of any Soviet bomber attacks across the Arctic Ocean during the Cold War. This task became obsolete when intercontinental ballistic missiles became the main delivery system for nuclear weapons. The DEW line was the northernmost and most capable of 3 related radar lines in Canada. NORAD's primary task is to alert higher command authorities and supervise the defensive operations of U.S. and Canadian fighters. The most important U.S. fighters associated with NORAD operations are the F-15 Eagle twin-engined air superiority fighter, originally from the McDonnell Douglas Company, and the F-16 Fighting Falcon single-engined air combat fighter, originally from the General Dynamics Company. Though these have been upgraded in their airframes and power plants, far greater emphasis has been placed on increasing the capability of their electronics and weapons. Here, military personnel load electronic countermeasures pod equipment onto one of the hard points below an F-16. This podded system is designed to test air defense radar systems. Modern fighters need to have a continuing capability against different types of jamming equipment. This is particularly true against the warplanes of any hostile power with an effective electronics industry and the skills to create potent electronic warfare systems. The NORAD complex at Cheyenne Mountain was designed to provide total security and a continued operating capability, even in the event of a direct hit by a nuclear weapon. The complex is completely self-sustained in all essentials, such as power generation, air recycling, and provision for extended habitation during and after a nuclear war. The complex can therefore be closed off from the outside world in times of crisis or war. The layout of the complex was designed to allow personnel to reach and man their stations as quickly as possible, and to take over from duty personnel with no disruption to the operation. Electronic defensive systems, generally known as ECM, can be built into larger warplanes such as bombers, or alternatively, they can be packaged into pods for carriage under the wing of smaller aircraft such as fighters. Podded systems are also easier to maintain, as they can be removed and taken into an environmentally controlled hangar. There, they can be readily serviced, repaired, or upgraded with new sensors and/or software to deal with emerging threats. Here, ground crew remove tag protective covers from ECM equipment on an F-15 fighter. Typical of American podded ECM equipment is the ALQ-131 pod, seen here below the port wing of an A-10 Thunderbolt II battlefield attack warplane. Another type designed to carry ECM pods is the AC-130 battlefield gunship variant of the Hercules tactical transport. This is another battlefield type designed for low-altitude service in the face of powerful ground-based weapons and can survive only with the aid of advanced electronic aids. The Boeing RC-135 is a U.S. Air Force reconnaissance aircraft used to support theater and national-level command authorities with on-scene intelligence collection, analysis, and dissemination capabilities almost in real time. In the background are Boeing E-3 Sentry airborne warning and control system aircraft, another vital component of the electronic warfare capability of the U.S. The RC-135S Cobra Ball is equipped with special optical instruments to observe ballistic missile flights at long range. The type is an extensively modified C-135, and the 4 aircraft are part of the 55th Wing 45th Reconnaissance Squadron based at Offutt Air Force Base, Nebraska. The Cobra Ball aircraft were originally assigned to Shemya in the Aleutians and used to observe Soviet ballistic missile tests on the Kamchatka Peninsula in conjunction with the land-based Cobra Dane and shipborne Cobra Judy radars. Seen with a Boeing B-52 Stratofortress strategic bomber, this Boeing EC-135 is a version of the C-135 Stratolifter transport. It has been modified to operate within the context of several U.S. Air Force programs, including use as airborne command posts for high-ranking officers. The cabin of the EC-135 provides the room for the mission equipment and mission crew of this invaluable electronic asset. It is crammed with all the mission equipment that the crew may require in the course of the long flights typical of this aircraft's duties. Here, an EC-135 lands after another lengthy mission. The EC-130 Commando Solo is a modified C-130 Hercules used to conduct psychological operations, or PSYOPs, and civil affairs broadcast missions in the standard AM, FM, HF, TV, and military communications bands. Missions are flown at the highest altitudes possible to ensure maximum coverage of enemy territory. The EC-130 is designed to undertake long missions with the aid of air refueling. A typical mission is based on one aircraft flying an orbit offset from desired targets. The targets may be either military or civilian personnel. The Commando Solo is operated exclusively by the 193rd Special Operations Wing based at Middletown, Pennsylvania. Here, in full combat gear, the crew of an EC-130 leave their bus and board their aircraft. The whole process of preparing an aircraft such as the EC-130 for a mission is time-consuming and difficult. But painstaking care at this stage is essential to survive in hostile conditions and to successfully complete the assigned mission. The ground and flight crews have primary responsibility for the aircraft before it takes off and once it is in the air. The mission crew in the converted hold is tasked with keeping the mission system running and putting out the signals demanded by higher command authorities. With pre-flight checks of the aircraft and its systems completed, the EC-130 takes off. It often operates comparatively close to a fluid front line, so takeoff and landing can be particularly dangerous periods of any such mission. Ground-based radars are primary targets for armed electronic warfare aircraft, while mobile units such as this present special problems. Against the backdrop of a Lockheed Martin C-5 Galaxy strategic transport parked on the ramp, a radar unit is seen in operation with its antenna rotating. Radars such as these are generally associated with air traffic control around and over an airfield. But the destruction of such systems can pay impressive dividends in disrupting an enemy's ability to handle their air assets in an effective and timely manner. This is mobile equipment with the radar data displayed on the screens inside a van parked nearby. This is a radar approach control unit, tasked to ensure the safe arrival of aircraft under almost all weather conditions, day and night. Inside the van, the operators watch their screens and talk to inbound aircraft by radio. Radar is one of the keys to modern military operations and a primary target for electronic warfare aircraft.